All right, well, good afternoon, everybody. This is the last session of the day, so thanks for sticking it out. I am confident that you will not be disappointed. We have a great cast of speakers coming up. This session is called Episodic and Catastrophic Events, so I don't think we need to go into detail as to what that means, but it's going to be a really good session. What we're going to do is we're going to try this a little bit differently. We're going to hold questions to the end. So after the speakers are done, we'll just go right into the next speaker. And then at the end of the session, when everyone's done with their presentations, we'll bring those that are here live back up on stage, and we'll have kind of a panel discussion. So without further ado, I would like to invite our first speaker, and that's Dr. Mark Luther. He is an associate professor and director of the Center for Maritime and Port Studies at the University of South Florida College of Marine Science. He's worked in real-time ocean observing systems since 1993 and was involved in the planning and implementation of the U.S. Integrated Ocean Observing System from its inception. He's also been sailing the water since 1983. He was also on my committee, and he's just a great guy. So he's going to talk to you about ship wakes in Tampa Bay and their potential shoreline impacts. Mark?
Thank you. Good afternoon. This session is on episodic and catastrophic events. Ship wakes certainly count as episodic events and are sometimes catastrophic events. I'd like to acknowledge my co-authors, Steve Meyers from the USF College of Marine Science, Gary Rollerson and Ed Sherwood from the Tampa Bay Estuary Program, Stephanie Ringuet, who at the time we did this was with Port Tampa Bay. She's since gone elsewhere. Katie Conrad and John Basili from the U.S. Fish and Wildlife Service. So again, the objectives of the study is to characterize wakes from ships transiting Tampa Bay, identify the source mechanisms, the generations of those wakes, how big are they, where do they go, what do they affect, where do they impact sensitive marine habitat, and how often do they occur. Our data comes from what's called the Automatic Identification System, or AIS. We got archived AIS data through the marinecadastre.gov website, which is a joint effort between NOAA and the Bureau of Ocean Energy Management. We did quality control and assurance on the raw data and filtered them, as I'll talk about in just a second. The data we looked at for this study was a 3-year period prior to 2015. The data were just a little bit sparse, but from 2015 through 2017, we had good data. But AIS, if you don't know about it, every commercial vessel over 20 meters in length or 300 gross tons is required to carry a transponder that broadcasts information about the vessel itself, but all its navigational information, its position, its speed and course over bottom, its draft, its length, beam, and all of that sort of stuff. So the AIS data set itself that we utilized had over 86.5 million individual data points containing the unique vessel ID number from IMO or its MMSID, or MSSID, its length, its draft, its beam, position, speed, direction, and vessel type. The AIS has over 100 different vessel types identified. We collapsed those to a finite number. As seen here, we collapsed all of the cargo carrying vessels into one class. That included container ships as well as break bulk and dry bulk carriers. Tanker ships are all liquid bulk carriers. Passenger vessels are primarily cruise ships, but include ferries and other passenger carrying vessels. Tugboats are various and sundry types. Fishing vessels, recreational vessels, enforcement vessels, research, supply, and other. Thing to note here is that this is the count of each of those vessel transits versus their estimated wake height. We estimated the wake height for each vessel based on its draft length, its hull characteristics, and its speed using some commonly accepted engineering empirical formula. And so this is the count scale is logarithmic, going from 1 to 10 to the 5. As you can see, the largest number of vessel transits were in the cargo class, given they're in the blue, but the highest wakes were generated by the passenger class, the large cruise ships shown here in the green. One interesting note in the recreational vessels, there's a little spike out at some high wakes. We trace that down to 3 mega yachts that regularly transit in and out of Tampa Bay, just for that little spike there. So next. So we calculated the wake from each of those 8.5 or 85.5 million vessel locations or vessel AIS transmissions, and then again using wave theory propagated those wakes onto shore and calculated the cumulative wake energy at every point along the shoreline of Tampa Bay for each year of that period. So shown here is 2016 and 2017. You'll note that the highest cumulative wake energy is out around Egmont Key and along the eastern shoreline of Tampa Bay. If you go to the next one, then working with TBEP, we were able to project that onto the shoreline classification. As you can see, by far the largest impacts on shoreline habitat is out at Egmont Key, and then along the eastern shore, particularly around Port Manatee, just inside the Skyway Bridge there, around the mouth of the Manatee River, and on the spoil banks up around northern and eastern Hillsborough Bay. Again, as those of you who've known me a long time know that this is kind of personal. I consider myself sensitive habitat as well. The vessel seen here nearly killed me with its wake. Well, I was told that I died 3 times, but I got better. So anyway, yes, so that's what I meant by ship wakes can be catastrophic. That's fine. So again, our primary findings were that the largest estimated wakes were produced primarily by large cruise ships because of their speed. They're typically the fastest vessels coming in. They maintain up to 22 knots until they get right up into Hillsborough Bay of speed. The cargo class vessels had the largest number of ships that produced high wakes. There's a lot of cargo that comes in and out of Tampa Bay. In fact, Tampa Bay is the largest port in Florida and one of the top 15 or 20 ports in the country by number of ship transits and tonnage of cargo or value of cargo transported. The enforcement class we determined was most likely to produce high wakes relative to the number of such vessels. However, in the AIS data, a lot of law enforcement vessels don't transmit AIS data because they don't want you to know where they are because they're law enforcement vessels. But they typically go very fast, particularly the small Coast Guard cutters that come in and out of Bayboro Harbor here. They're typically at full throttle whenever they're on the water and producing some fairly large wakes. So again, as we saw in the graphics, the eastern shore of Tampa Bay receives the most wake energy compared to the western shore of the bay. Egmont Key is subject to the highest number of ship wakes and the highest cumulative wake energy, primarily because of its proximity to the ship channel. If you've been out to Egmont Key, you can spit at the ships and hit them as they come past. And because they're just entering the dredged portions of the bay, they're typically going much faster there than they are going farther up the bay. Large vessels moving through very narrow waterways, such as the Alafaya banks, are not represented very well by this empirical formulation because there the channel is very narrow and surrounded by very shallow flats. And so the vessels that are going through there are displacing a significant fraction of the volume of the ship channel. And there's more like a tidal wave effect from those ship wakes rather than a ship wake that radiates away from the rear of the vessel. So again, the methodology developed here, though, can be applied easily at other locations. So, We'd like to extend this analysis to include more recent data. We now have good data for 2018 through 2020, and we have a new partnership with a company called Polestar Global. They are the provider of vessel tracking information to the U.S. Coast Guard, other federal agencies in the U.S., as well as 60 other maritime nations around the world. And they just located their headquarters right next door to us over here on Bayboro Harbor at the new Maritime Technology Hub, as we're calling the old SRI building. So we're working closely with them. We have access to all of the AIS data that they collect from around the world. Again, we want to apply improved analytical and numerical methods for computing those vessel weights and to characterize their propagation towards shore. We've gotten some pushback from the maritime industry to look at the relative contribution of wind-generated waves to ship weights when it comes to impacting marine habitat. So we'd like to do some more studies to pick that apart. So a long series of relatively small wind-driven waves can have as much cumulative energy as just a couple of large ship wakes. But again, it only takes one or two large ship wakes to do some significant impacts to coastal habitat. So again, we want to quantify that. And to that end, we plan to, or Pinellas County and the Estuary Program has purchased some higher resolution, longer duration wave sensors for another project that we're working on with living shoreline characterization. So when that project is done with them, we plan to use those to look more in depth at this. Also to look at the shoaling effects of waves as they come into shallower water. So again, just to illustrate those points, this is the AIS data that we have for 2015 through 2020. And you see that there's not much long-term change in the number of unique vessels, that is, individual vessels that make multiple transits in and out of the bay. The lower plot is the actual number of vessel transits, again, for just vessels greater than 30 meters or 100 feet. So you see a slightly downward trend in the number of transits, a dip during the pandemic, particularly in the passenger class vessels. But again, overall, the total number of vessel transits has not changed very much. And so this is that wave array that we've constructed with equipment purchased by Pinellas County and the Tampa Bay Estuary Program. Consists of rapidly sampling 8 to 16 hertz sensitive pressure gauges in each corner of a 2-meter square array with a data logger, and then a large external battery pack to allow us to get up to 30-day continuous sampling at 4 to 8 hertz. Because to distinguish ship wakes from wind waves, you have to sample continuously. Typically, wave sensor systems will take 20 or 30-minute bursts of samples, then calculate the wave statistics, and then 30 minutes later start another burst. Well, if you're looking for ship wakes, you can't count on a ship wake coming through during that 30-minute burst. So that's my signal to quit. Oh, there we go. Which is fortunate because I'm about ready to quit. So again, we hope to be able to put these out and we can also get wave direction so we can distinguish incoming versus reflected waves. So with that, I thank you for your attention and end with a picture of a Coast Guard cutter and a tugboat kicking up huge wakes.
Thank you, Mark. We'll save questions to the end. I know I've got a few. So once we're done with our speakers, then we'll go ahead and have kind of an open discussion. So the next speaker up is none other than Ed Sherwood. I don't really think Ed needs an introduction, but he's been the executive director of the Tampa Bay Estuary Program since 2018. He has been actually, you've been a program scientist with the program since 2008. So no stranger to the Bay Area. And what he's going to talk about today is coordinated monitoring of the Piney Point wastewater discharge into Tampa Bay, data synthesis and reporting.
So you all made it through to the last session on Thursday. So thanks for sticking around and hearing the presentation. So way I was going to frame this came to me probably around like 2 o'clock last night as I was thinking through what I was going to present on and provide information on Piney Point. You guys are probably tired of hearing about Piney Point, right? I'm kind of tired about speaking about Piney Point too, to tell you the truth. So this presentation is primarily focused on that event response to the Piney Point discharge that occurred last year, but also how we used open science tools to help us bring people together, collect information quickly, and disseminate just as quickly. So really that's the focus of this talk. All the credit goes to my staff for all the work that went into the response last year. Dr. Marcus Beck actually put this presentation together for me in lieu of all the planning and coordination we've been trying to do this week. That really helped me out. So we're going to go through it. Go ahead, Mark. So I don't have to kind of go over this story. You've all heard this before, right? Nitrogen is king in Tampa Bay. We've been trying to reduce nutrient loads to Tampa Bay for a long number of years, since the inception of the program in 1991 and even earlier, before the program was even founded. So that started with significant reductions of wastewater from many of the municipalities surrounding the bay through the Grizzled Fig Act, and from there we did a significant kind of at a loss right now because this has been a very challenging basis 7 for us, and it's come to the point, you know, where we've been working together so collaboratively for so long in the Tampa Bay region that I'm in fear that that might be starting to break down, and I want us to get back on the same page. And really that's what we're trying to achieve through the Tampa Bay Estuary program and everything we're trying to do in this region. So, you know, from that standpoint, we're thinking about collecting information differently than has been collected in the past, and we're trying to utilize that information in a whole lot meaningful way and get it to resource managers quickly. So if you go on to the next slide, you know, the Piney Point event really brought out that need to get information out quickly. We live in a free and open society where information shouldn't be hidden and needs to be shared. And that's what we're trying to do through these initiatives. So Piney Point was a significant load to the Tampa Bay watershed. Over a 10-day period, discharged about 205 tons of nitrogen into lower Tampa Bay. On an average monthly basis, that about equated to the same amount of loads that were going into all of Tampa Bay from stormwater loads, about quadruple the amount coming from point sources, about quadruple the amount coming from atmospheric deposition. So that's a significant load to Tampa Bay and on a really small time scale that we knew was going to have an impact. And that's the focus we need to think about moving forward, is continue to control nutrient sources, reduce nutrient sources to Tampa Bay, because you saw the ill effects of that last year. And that's pretty much highlighted in this infographic. From the data that's collected all of last year. And you know, this is our way to interpret a lot of that scientific information and quickly relay that to the community so that they understand when I throw out jargon and misinterpret things, that they get a clear picture of what actually happened in Tampa Bay in response to that nutrient load, that anomalous nutrient load that occurred. And really, why we're all here still is because we care about the Bay, and why we were out there continuously on a bi-weekly basis responding to an event like that is because of all the progress that was made in the Tampa Bay region over these past 30 and 40 years to get the bay's water quality back to where it was before we had a lot of nutrient discharges. So, that sense of collaboration, I was heartened to see. It brought me a great sense of gratification to see people come together to understand what those potential impacts could be from nutrient loads. And, the community responded. And that's very gratifying for me to see. And that makes me happy to see that we could still work together towards these common solutions and hopefully put an end to some of these discharges in the future that, have the potential to cause impacts and significant impacts to Tampa Bay. So I'm hoping I'm not rambling because I'm sure I'm going to go way past time. But go ahead.
You're good.
So, that's how we kind of formulated our response internally. We relied on you all to be out there monitoring on a consistent weekly basis so that we could understand what the hell was going on in Tampa Bay during this event. And our role and how we filled our role in the region was to assimilate that information and quickly get it out so that people that were concerned about the bay's condition knew exactly what was going on. And those were the things that we dealt with internally in terms of collecting all that information from a lot of disparate sources. Our water quality monitoring groups within the region have done great works on coordinating their regional ambient monitoring program so that when we do collect information, it's consistent and comparable when we have events like this. So I heard this term last week at the UF Water Institute. We used sort of the approach of a data lake using Google Drives to get partners to put this information in one common place. And from there, we used open science tools, our wrangling, largely done through Dr. Marcus Beck, to quickly wrangle that data, do some rudimentary checks. Again, we're very reliant on all of the ambient monitoring programs sitting in this room, being part of RAMP and collecting consistent and comparable data so that when we assimilate that information in these sources and put it up on the website, that we had a great level of comfort of the results we're seeing. If you go on. The next sort of steps, and you could advance to the next one, that we thought about was, those peaks on the left might make sense to me in my head, but they might not make sense to everyone that are seeing that information. So we're very reliant on a long-term record to understand what normal conditions in Tampa Bay were. And that's really what we were highlighting in terms of those purple boxes. Those are the ranges of water quality conditions that are typical in Tampa Bay during these monthly periods. And those outside observations, we're really in need of a comparison to regional baselines. So again, I think Marcus created some great algorithms to quickly match stations collected during this response to the long-term record to see how comparable those data were this particular year to that long-term information that we garnered. And that, I think, gives us great confidence to say that we had water quality much different in 2021 than we have had in the past. And this graphic sort of highlights all the data collected on a weekly basis. Particularly, our nutrient of concern is total nitrogen. And we saw, particularly in and around the Piney Point region, Area 1, higher total nitrogen concentrations immediately after the event, and then subsequently, through time, through the end of September. again, above normal, those blue bars on the top left. That response to the nutrients was, sorry. So that response to the nutrients was manifested in chlorophyll A conditions initially through a diatom bloom. It was non-harmful diatom bloom shortly after the discharge ceased in April. We saw a little bit of subsidence, potential improvements in water quality, but then we saw this reinvigoration of other higher chlorophyll conditions, and that pretty centered around when we saw red tide enter into Tampa Bay and start to take off. So these graphics sort of highlight that transition over that time period. Go ahead. So those graphs are pretty useful to me, again, in my head, and they make me make informed decisions about what we need to do to make forward. But sort of the second step of using that data was, exposing it to the community so they could actually really investigate it, drill down to the nutrients, each of the data collection points, and make their own assessment of what the data is telling them. And that's, again, where we really had a valued contribution from Dr. Marcus Beck of creating these dashboards. These dashboards, again, put all the information in one place in an effective way that everyone in this room as resource managers can utilize it. And our goal was to not rely on any one data source. We recognized all the effort that went into responding to the Piney Point discharge, and we wanted to use that information as much as possible. So if you go on to the next one, again, that dashboard is useful because you could look at any one of those particular data points in response to the Piney Point discharge that were collected during that very intense sampling that occurred over that April through September period, and drill down at one particular site using those algorithms to match to a closest long-term station to really understand how different the base conditions were in 2021. This area just reflects an area where we know we had some red tide intensification, and it really matches to that period of time in early July when we did have some significant fish kills throughout Tampa Bay. And that bloom was pretty anomalous in terms of stretching all the way into Hillsborough Bay and Old Tampa Bay. I think we've said it before, it was not something we've seen in these parts since the early 1970s. And that's not a place we need to get back to. We need to continue to move forward and work together towards reducing nutrient loads so that we have clean water quality to improve seagrasses. So Maya, the lessons learned through all this is that when we use these open science tools, we could have a vast information source to make really informed decisions about what needs to be done for these lingering issues that we have in our region. And the other lessons learned, we've used the regional ambient monitoring program data for so long in Tampa Bay that we kind of take it for granted. But that was just as instrumental to this response as everything that went into the biweekly and weekly sampling that was done in response to the discharge event. But all the data goes for naught if we're not actually providing it to the public, but providing it to the resource managers and utilizing it to better manage Tampa Bay. So I think I'll leave it there. I think I don't have any more time, but please reach out to the estuary program. Thank you to all the partners that took the time to monitor, to provide us the information and allow allow us to share it to the public in a meaningful way that will hopefully evoke some change in terms of finally and fully closing out the Piney Point facility, because I think that's what everyone wanted when they're out on the water seeing the impact. So I'll stop there.
Thank you, Ed. I'm gonna invoke my right as session lead to just make some comments to Ed. Thank you so much for everything that you do and the estuary program does. So I work for the Water Management District, and I can tell you, and I've been working in Tampa Bay for 20 years. I could not do my job without the work that the estuary program is doing. And I think most of you, if not all of you in this room, would probably share that sentiment. So yeah, I mean, give it up for the estuary program. I mean, this is a very interesting time in history, and we are seeing changes. And, you know, there's the old cliche, what got you here won't necessarily get you there, but we're doing it together, and that's what's really important. So having said that whole togetherness thing, we're going to move south to Sarasota Bay, and we're going to still hit the Piney Point event, but this time we're going to hear from Dr. Dave Tomasko. So since fall of 2021, Dave's been the director of the Sarasota Bay Estuary Program. Prior to that, he was in the private consulting world for over a decade. Can't believe it's been that long. And that was previous to that, he was the manager of the Southwest Florida Water Management District's then known as environmental section. And he was also with the SWIM program, which is the program that I'm currently in. I consider Dave probably one of my biggest mentors, and he still is that to this day. You know, he was also, and this is a really important thing because I think, you know, things kind of go full circle. Dave was the first environmental scientist for the Sarasota Bay Estuary Program, and now he's back as the director. So he's going to talk to us about impacts to Sarasota Bay from Piney Point, examining the evidence. So hopefully, Dave, you're out there in the virtual world, and I'll give it over to you.
Hey, can you guys hear me?
Yep. Hear you
Cool.
good.
So sorry if my voice breaks. I really wish I was there, but I'm pretty sure that you don't want me there. So, but nonetheless, let me get going. So we're going to talk about Piney Point a little bit, impacts to Sarasota Bay. This was a very big issue. I think what you pick up listening to Ed is the same thing. Hopefully you pick up from me, which is we're pretty passionate about our two systems, and we're concerned about them. And the level of stress that they're under is something that's a little bit scary right now. You've also seen there's an awful lot of great talent applied. You saw earlier the work that Jennifer Shafer was doing with the playbook, and it's a phenomenal tool. But it's for Sarasota County. It's not for the rest of our watershed. And so what we have to balance is not only what happens in Sarasota Bay from Sarasota County, but what happens from Manatee County, its influence, the city of Bradenton, town of Longboat Key, but also it appears things that are outside of our watershed boundary, which is Piney Point. So let's get going. Next one, please. So this is what we monitor in Sarasota Bay. When I say we, I mean our collective group. Manatee County, Sarasota County, and Marine Lab collect water quality data. FWC collects fish data. The Water Management District does seagrass mapping. Us and volunteers and county staff do seagrass transects. Everything here that we show here that responds to nutrients is monitored, and it's part of our report card. And our report card says we need about a 20% nitrogen load reduction. That's 92 tons of total nitrogen, maybe 12 tons of dissolved inorganic nitrogen. So all of this stuff is measured because all of this is stuff that can, you know, bring about an adverse impact to Sarasota Bay with nutrient loads. Next one, please. But the focus of traditional monitoring efforts is phytoplankton. And this is important because in the early stages of Piney Point, when we were trying to figure out what the hell was going to happen, we had people from fairly high levels of, you know, state government basically making the comment that they didn't think it was going to be that big of a problem, limited in scale, limited in duration. And I was told it did not affect Sarasota Bay. And I just don't believe that that was accurate. And we're going to go through some of the data to talk about why we think it wasn't accurate. Next, please. So this, you've seen this graphic before. This is from Bob Weisberg's modeling group from University of South Florida. It shows the it shows the plume from Piney Point. For those of you who don't know where Sarasota Bay is, it's everything south of Tampa Bay on this particular graphic here, and it doesn't include the southernmost portion. But the areas that we see that kind of like in the southern part of the extent of that plume, that is Anna Maria Sound, is the open water that's connected directly to Tampa Bay. And that little kind of pocket off to the east there, that's Palmasola Bay. And if you look at that, you can see this is a log 10 scale. This is for May, so it's a little bit after the first plume. But you can see most of Tampa Bay and the northernmost parts of Sarasota Bay are influenced by this plume. But you can also see that, you know, the vast majority of our area that's influenced is like in that kind of like blue-green area, the kind of yellowish green. I think it's called chartreuse, and that's 1,000-fold dilution. So why in the world would we be surprised or concerned about 1,000-fold dilution? Well, next slide, please. So let's do some math here. Piney Point's nitrogen concentration, it not only loaded 200 tons of nitrogen, it loaded it in inorganic form at 200 milligrams per liter of nitrogen. The worst performing wastewater treatment plant in our watershed is 20 milligrams per liter. So 200 million gallons, if you turn that into the functional equivalent from wastewater, it would be as if it was 2 billion gallons of the worst wastewater effluent produced in our watershed. So 200 milligrams nitrogen. Our background values are 0.4. So you can do this math in your phone. 1 gallon of 200 mixed into 999 gallons is 0.4. Resulting 1,000 gallons is 0.6. And what that means is that 1,000-fold dilution is still enough to get you a 50% increase, which is enough to get you an algal bloom. And that's an algal bloom of various forms. It doesn't have to be just phytoplankton. That's what we're going to talk about, because that's not all we measured, but that's not all the impact was. Next one, please. So this graphic, maybe you've seen it, I'm not positive, but this shows phytoplankton values, chlorophyll concentrations, and the values that have the circle on the outside represent a value that is outside of the mean plus 1 standard deviation. So a mean plus 1 standard deviation in a normal distribution would mean 16% roughly of the data. 1 divided by 0.16 is 6. So in other words, generally you'd expect to see 1 out of every 6 of these circles with a little outline around it, because that would mean 16%, 1 out of every 6. But you can see that there's an awful lot more than 1 out of every 6 of these circles has a little circle around it, which means that it is not by chance alone that we're outside of the normal range for so many of these locations going down into Sarasota Bay in those areas where we know that there was also an effect from Piney Point from the USF model. Next one, please. But then we had this happen, and I've been working in Sarasota Bay for 30 years, Tampa Bay for 35 years, and I've never seen anything like this. Always seen Linguet. Linguet is not uncommon. Blue-green algae have been around for billions of years on this planet, but I've never seen Sarasota Bay look anything close to this. On the left-hand side is one of our transects, and this is one of those field days where you're hoping that nothing actually awful happens to you when you get out of the water. That white structure there is like a float on the tail end of our transect. And between that and the mangroves, that's not a mudflat. That is this Dapis cleosa, also known as Linguet, also known as mermaid's hair, also known as fireweed. Fireweed because it causes contact dermatitis. Feels like you're rolling around in attic insulation when you get out of the water there. And look at the color of that water, that silvery look that's so full of bacteria, no oxygen in it. So this Linguet bloom that we had was all over the place in Anna Maria Sound. Next one, please. This is what it looks like underneath the surface. So it's growing entangled within the seagrass right here. And so what you see on the surface is actually one of the tail end of its growth cycle, because it's actively growing in the bottom. And you see those little circles there? Those are oxygen bubbles that are being produced by the massive amount of photosynthesis that's occurring by this photosynthetic organism. And those air bubbles, those oxygen bubbles, lifted up to the surface. Next slide, please. And this is what happens to your seagrass meadows. They don't become a nursery ground, they become a killing ground. And so we have no oxygen in these areas where this Linguet is decomposing. It accumulates, you can see fish kills. It smells horrible. It smells like someone had popped open a refrigerator, full of stakes after it's been unplugged for a couple of days. And next slide, please. This is what it looks like for people who live along the waterfront. On the left-hand side, it smells like sewage, it looks like sewage. And this picture on the left was taken by the mayor of Holmes Beach. She's not a happy woman when she looks out and she sees this along the waterfront property owners, the businesses, the bars and restaurants and marinas that you see on the right-hand side. So this bloom affected more than just the ecology of Sarasota Bay. Next, please. So we didn't have a huge amount of data in Tampa Bay or in this part of Sarasota Bay. So we went out and we started collecting it. And Ed and I, just to take a break from all the stress of it all, we went out to visit a lot of these sites. So the area in red, this is where this data comes from. That was the place called Clam Bar Bayou, something like that. And so Ed and I collected the first data sites, first data collected there. And then you can see the continued data. So let's just focus on the bottom part of that table, which is macroalgae. Those little dots mean that there wasn't any macroalgae found. In fact, there was hardly any macroalgae found, which was a good bit of information. You know, we were fine and right in the area, not that far away from Piney Point. Not a lot of macroalgae. So initially, seemed like good news. Next one, please. So this is from another spot. This is around Joe Bay. This is not that far away from where there's a commercial clam lease. And again, you can see on the bottom, the little dots for macroalgae. There's just not an awful lot. So it kind of looked like, you know, from the sites that we visited in that lower part of Tampa Bay, and there were other areas that did show algal blooms. It kind of looked like maybe we just, you know, dodged a bullet, that we actually didn't have the kind of macroalgal blooms that might have actually been brought about by this nutrient load. Next one, please. But in Anna Maria Sound, which I just showed you earlier, that's where we started to see a lot of cyanobacteria. A lot of this, the cyanobacteria is Dapis pliosa, aka Lingbia. And you can see that in June 3rd, you see the big diameter blue circles, meaning we had cyanobacteria levels at, it was 100%. It was actually more than 100% because it filled the water column. It not only covered the entire bottom, but it filled the water column. You actually had to swim through this like you're swimming through some sort of weird kelp forest of stinging nettles or something. And that's what it was like in that system. 76 to 100% and in June. Next one, please. This is another site, but one of the other things we saw is that it tended to like not last too long. It was only there for maybe a couple of weeks. By the time we got to mid-July, you can see that we start to see this pretty substantial reduction in cyanobacteria levels at this other site in Anna Maria Sound. So next slide, please. So Upper Sarasota Bay fits in Area 3. So Area 1 is kind of like right close to Piney Point. Area 2 is upstream of it, if you would, inland of that. And Area 3 includes all of Sarasota Bay samples, but also Terracea Bay and Manatee River. So now get across the categories of Area 1 and 3. Next, please. So let's look at the top graph. The top graph is macroalgae. Area 1 is around Piney Point. Area 3 is around Sarasota Bay. And look at the light blue circles, and you'll see that we had the similar pattern, but actually even higher abundances, higher amount of coverage and frequency of occurrence in Area 3, not by much, but a little bit higher than what we had even in the area that was right adjacent to Piney Point. And it also then goes down. You also see this overall pattern of macroalgae decreasing because in our waters, macroalgae is typically very high in the wintertime because that's when our water is clear and macroalgae grow on the bottom and they need water clarity for them to grow. But we have a lot of macroalgae in Area 3 across all the stations. If you look at the bottom part of those graphs and the white circle that's on the top, that is total seagrass coverage. And you can see the good news is it appears that both in Area 1 and Area 3, we don't find evidence that this cyanobacteria infestation caused a long-term decline in seagrass coverage, perhaps because it occurred in some of the early parts of the warmer times of the year. It didn't occur in August and September. It was actually kind of gone by the time we got to July. Next one, please. So a little bit of evidence that we were more of a hotspot really than Tampa Bay in general. Anna Maria Sound had about 5% of the stations, but we had almost 11% of all the high biomass stations for macroalgae. Tomasko Bay, which is that little thing off to the right, 3%, but 5% of all the high biomass stations. And in fact, of all the stations that said, hey, there's Linguet here, a third of them were in Anna Maria Sound. So upper Sarasota Bay was more likely to be infested with cyanobacteria than most of Tampa Bay. Next, please. But like I said, we went out to these stations, and then like 2 months later, or 2 weeks later, excuse me, the cyanobacteria is gone. It's not completely gone. Some of it's still there in the bottom. And in fact, if you weren't from this area, and we had listened to people who actually weren't from this area, they might say, well, what do you complain about? Look at it, it's gone. But when you look at that water on the right-hand side there, that is not what Sarasota Bay is supposed to look like at the end of the dry season. It's not supposed to look like that at the end of the wet season. So that water is really green. Next slide, please. And in fact, that is the point that we're trying to make. We had a phytoplankton bloom and cyanobacteria bloom. And again, you should expect to see 1 out of every 6 of those on average be a circle, a border around it, because outside of one standard deviation. And instead in Sarasota Bay, it's well over half of them. On the right-hand side is some really neat work done by Marcus Beck that shows modeled chlorophyll as a function of nutrient load. And the far left side there, that dark purple band there, that's what we started 2021 with. So we started off our wet season with much worse water quality than we would normally expect to see in our system as a whole. Next, please. So one of the reasons why we're concerned about this is because that area where we had the cyanobacteria, the phytoplankton, is right on the edge of the area where we've lost 2,000 acres of seagrass. And that's the area that shows in the dark red there. This is one of the prettier parts of Sarasota Bay. The visibility right now is 12 feet or so. But we lost about 2,000 acres of seagrass. We think because of the 2018 red tide, the 2017 Hurricane Irma, and the 2016 red tide as well. So red tide, hurricane, red tide, all of them occurring in the warmer times of the month, warmer times of the year. Making it dark when it's warm is a bad thing for seagrass. So that is just on the edge of where we had already lost 2,000 acres. Next, please. And it falls within this category. The things that we saw in Tampa Bay are not just in Tampa Bay, but we saw kind of 3 things happening. We had a regular phytoplankton bloom. Now we had this cyanobacteria bloom. Then we saw a red tide. The red tide in Tampa Bay was the worst one in that part of the bay in 50 years. But we didn't see that in Sarasota Bay. Next, please. But we're concerned about it because the language we use is that humans don't cause red tide, but we can cause it to be worse. So why would we make it worse? Next, please. This is what it looks like in Sarasota Bay when a red tide comes in there and you don't have it loaded with nutrients. You have nice blue water and then you got red tide. And so that red tide is there, but it's not going to explode the way it did in Upper Tampa Bay. So last slide. Do we think there's a potential link? And yeah, we do, for a couple of reasons. We had phytoplankton and cyanobacteria blooms. We have problems in Sarasota Bay, absolutely, but not as bad as we had it. And the cyanobacteria and phytoplankton were pretty much limited to the areas where we had the plume influence. Number 2, the nutrient mass required. We came up with some estimates of how much nitrogen is probably in that cyanobacteria bloom. And if it was a lot more than came out of Piney Point, it'd be a little bit silly to blame it on that. And the answer was it wasn't. Only about 20% would be required for a worst case scenario. So it does make sense it could be there. And then the last thing that we end with is this matches up really nicely with work done in Roebuck Bay in Australia. The time lag between the nutrient load and the Linguet bloom that we saw was about 2 months. That's almost exactly what was found in Australia as well, because you need the nutrient load, but you also need clear water and then warming temperatures. And that's when the nutrient load manifests itself in Linguet. That's what we think happened in our system. And with that, I'm done, and we can have questions near the end if there's time. Thank you very much.
Thank you, Dave. Hopefully we'll have some time at the end for some questions. So we'll jump to the next topic. So we're going to move a little bit away from Piney Point, but perhaps not too far away from what Dave and Ed were talking about. This talk is presented by yours truly. I'm Chief Scientist for Water Quality and the Seagrass Mapping Program Lead for the Southwest Florida Water Management District. And what I'm going to talk about today is something called the hangover effect. I don't see Jay in the audience, but this was a term that was coined by Jay Leveroni of the Sarasota Bay Estuary Program about, I don't know, a little over 2 years ago. So I want to start with the Webster's definition of what a hangover is, and there's two. So the first one is something that remains from what is past. The second one is a disagreeable physical effect following heavy consumption of alcohol, perhaps a harbinger of things to come, who knows. So what I'm going to present to you today, I'm going to use Charlotte Harbor as a case study, is a little bit of a different definition of a hangover. So I'm defining a hangover today as a disagreeable physical effect in an estuary following heavy consumption of available nutrients by macroalgae. All right, so we're going to go down south to Charlotte Harbor. For those of you who are not familiar where Charlotte Harbor is, this is kind of the west central Florida coast of Florida. That orange line is the boundary of our water management district. We cover about 16 counties. And these are what we consider 12 swim priority water bodies. Number 5, which is all the way down south, that's Charlotte Harbor. So that's the system that we're going to talk about here today. Next slide. And what is special about Charlotte Harbor? Well, number one, it's the second largest open water estuary in Florida. So it covers about 700 square kilometers. That's kind of the open water area. The other thing is it has a really large watershed to open water ratio. In other words, so the ratio is 12:1. So for every square mile of open water, there's 12 square miles of watershed draining into this estuary. And that's a lot. So to give you kind of a perspective, Tampa Bay, the ratio is 6:1. Sarasota Bay, it's even smaller, about 3:1. So large watershed, lots of water coming into the harbor. And a lot of that water is very organic rich. So that presents its own challenges when you're trying to manage a system like this. So what we in SWIM have done really since the beginning of our program some 20, 30 years ago is we've applied what we call a hold and line nutrient strategy for Charlotte Harbor. Reason being that at least up until 2017, we really had not seen any evidence of degrading water clarity. We haven't seen any evidence of increasing chlorophyll A or increasing total phosphorus or total nitrogen. So overall, the sort of the consensus was that this system is a relatively healthy estuary, but that is not to imply that it is pristine. In fact, I don't know of any place in Florida that I would consider truly pristine. Gene Turner and others back in 2016 did a really good study. They did some paleolimnological work in Charlotte Harbor, and what they found is that in 2000, the nitrogen loads were 3 times greater than what they would have been in the 1800s. So, and that's an important point when we move on through the talk, because I don't want to give the impression that Charlotte Harbor, because we consider it relatively healthy, is pristine. By any means, it's not. It's not Indian River, but that's kind of a low bar. Sorry, Dwayne, if you're in the audience. Okay, next slide. So one of the things that we do, and we've heard this before about seagrass mapping as being a really important element to resource management, because it's a good way for us to kind of take the pulse of an estuary. And the district's been mapping seagrass since 1988 in Charlotte Harbor. We do this via a photo interpretation of aerial imagery that's flown specifically for the purpose of mapping seagrass. So it's a large program that we have. You can see we cover really the whole central west coast of Florida, and it's a very robust program. It's really evolved over the years. I don't know if Tom Reese is still here. Tom was kind of the godfather of the program. Dave Tomasko had it for years. Aaron had it, Aaron Brown. So I think everybody in this room has been touched by this program, at least at some point in time. So anyway, why that's important here, next slide, is because it is a good indicator of overall health. It's not the only indicator, but it's a good indicator. And so this graphic shows you what seagrass, the distribution of seagrass in 2018 for the harbor itself. And we segment the harbor into smaller segments, basically to give us kind of a better view of what's going on in different parts of the harbor. And you can see overall, since 1988, We've seen a bit of a rise in seagrass acreage overall, but you know, there hasn't been like this big increase like you've seen in Tampa Bay, this huge recovery from, you know, this state where it was really degraded. The harbor has by and large stayed relatively consistent, at least until 2018. Now we'll fast forward to 2020, and much like what Dave just showed you in Sarasota Bay, we saw some pretty significant losses of seagrass in Charlotte Harbor between the years of 2018 and 2020. But next slide, what I want to really focus on is this area that we call the east wall. So that's where most of that red is concentrated. And so those are the areas where we lost the most seagrass. We lost almost 50% of our grass along the east wall. That equates to about 1,700 acres of seagrass. And so that was a big shocker when we saw that. Now, in addition to this loss, we also saw another phenomenon, a concurrent increase in the amount of macroalgae. And so this is a picture actually from 2020. This is Dave, I believe one of them is Dave Blewett. This is FWC staff going out, and you can see just a lot of algae out there. And this was not only confined to the east wall, this was in other parts of Charlotte Harbor as well. But what this algae is, even though I swear to God, it looks like Catamorpha, they tell me it's Caulerpa fastigiata. Now, that was kind of a new one on me. It's not that it hasn't been around, but to see it in this abundance is very unusual. So big loss in seagrass, and then a big increase in this algae. So, you know, the question really is why? Next slide. I just want, before we get to that, I just wanted to show you also some other data that was collected by the Charlotte Harbor Aquatic Preserve. So this is data that was collected up to 2021. What I'm showing you is just one site along the east wall, and they do collect multiple sites, but this I think really kind of brings home the point. Next slide. You can see this sharp rise in macroalgae abundance based on the Brun-Blanquet, modified Brun-Blanquet score, 1 to 5 or 0 to 5. And then you can see that kind of subsequent drop in seagrass as well. So there's a lot more going on in these data than I have time to talk about, but I did want to just point out that you can see along the east wall, those green circles are 100% abundance of Caulerpa fastigiata in those quadrats that they use to collect those data. So question is why? First thing we do is we kind of look at the history of what happened, what was going on. Let's put this in context, right? We talked about context earlier. Hurricane Irma, September of 2017, passed through the area. The eye of Irma is about 30 kilometers from the west wall. When it came on shore, or at least by the time it got up to this area, it was still a strong Category 2 storm. So it was putting out maximum winds of 105 miles per hour. So big storm came through. And the graphic on the bottom left is an important one because it kind of brings home the point that, as I said earlier, Charlotte Harbor is not to be thought of, or even was not to be thought of, as pristine. So these systems were impacted by human activity, as is just about any place on Earth. And so this whole concept of sublethal stress is really important when you talk about these catastrophic events like a hurricane passing through. Hurricanes have been going on for millennia, so there's no reason to believe that the passage of a hurricane was enough to cause this 50% reduction in grass and this huge explosion of macroalgae. So what happened after that? I think, I don't know how many variations of that top left panel I've seen over the last few days. This was from September 1st through the 30th of 2018. But obviously we all know there's no secret. Red tide. NOAA just released a report, I think it was about 3 weeks ago. This was the worst red tide on record for Southwest Florida. And you know, I don't need to go into detail as to what happened, but it was a big deal. But there's one thing to keep in mind. Next, Charlotte Harbor itself was largely spared the brunt of this red tide event. So it was really bad along the coast, up and down, but the harbor itself was mostly spared. So again, we go back to this question of why. This red tide event potentially isn't enough to explain why we saw what we saw along the east wall of Charlotte Harbor. So what happened? Next slide. Here's what we think, and this is a hypothesis, so I don't have confirmatory data. It's very coincidental, but I think it makes for a good story. So this is sort of what we think is going on. So post red tide decomposition, we talked a lot about nutrient cycling over the week. What we think happened is after the red tide event, okay, here's where the hangover comes in. You've got all these nutrients that are out there caused by things like dead fish. Where do those nutrients go? So there's some work that was done by Dye et al. In 2020, and they did some circulation dynamic modeling in Charlotte Harbor. And what the one to pay attention to is the right-hand panel and go all the way down to the bottom at day 20. And what you see is you see a progression of these particles that get entrained along the east wall. Now, this is not news. We've known this for 30 years. There's been modeling that was done back in the 90s that show the general circulation pattern of Charlotte Harbor is in a counterclockwise direction. Most of the surface water and the fresh water comes down from the Peace Mayaca River, goes down the west wall. So what comes up the east wall? Well, in many cases, not always, but in many cases, it's water that comes in from the south and even from the west. So we think that this could explain largely what we saw in terms of that loss of seagrass and that explosion of algae. Next slide. So the other thing that I wanted to do is kind of link this to water quality. So what was going on in terms of water quality? And I keyed in on ammonia because ammonia seems to be one macronutrient that's really important if you're a Caulerpa fastigiata or prolifera trying to make a living out there. So ammonia released from decaying fish can be a significant nitrogen source. There's some literature out there, and there's a growing number of literature out there that supports that, and that Caulerpa prolifera, this was a paper that came out in 2020, showed that 81% of the total nitrogen acquisition is in the form of ammonia. So ammonia may be a tracer, if you will, to try to explain what was going on. So if we look at the historical data, or if we look at the data from 2014 to 2020 for ammonia along the east wall, and those little yellow dots are the stations where these data come from, you see this big spike. Didn't happen in 2018 during the red tide, it happened afterwards. So that's a really important, perhaps, takeaway message that, the red tide itself may not have caused this, the hurricane itself may not have caused this, but what happened afterwards may have. Next slide. So what I wanted to do is I wanted to capture kind of, put in context what that nitrogen concentration may look like. So I used 2,000 tons of dead fish, which I looked around the various media sources, and that seems to be roughly the number of total fish that were harvested during the red tide event, primarily, I believe, in Shoreline and Lee County and Sarasota, Manatee County. So that's not to say there were 2,000 tons of dead fish on the east wall of Charlotte Harbor. The fact is we don't know how many dead fish, how much decaying material was there, because we weren't collecting it. Where were we collecting the fish? On the beach. So that's where I got this number. So I used this number to calculate, and this is the calculations that I used were based on some work that Tampa Bay and Sarasota program have been working on. But the bottom line is I came up to 12,701 kilograms dry weight of total nitrogen load. To give you a perspective of how much of a load that is, if you take the total gauged load for the Peace Mayaca rivers and you divide that by 12, this number represents about 10% of the monthly load to the entire harbor from that big watershed. That's that 12-to-1 watershed. So that is not an insignificant amount of nitrogen. Further, if through remineralization, this nitrogen is coming in the form of ammonia, that may explain what happened. Now, there's one other thing I wanted to just bring to your attention as well, and this was based on some work that Dave Tomasko did a long time ago, and then some stuff that Jim Forkern and Jay Zeman did back in 2002, looking at thalassia specifically. But I wanted to also look at the amount of dead seagrass. Does the dead seagrass itself form a load? And so 1,760 acres is about what we lost along the east wall of Charlotte Harbor between 2018 and 2020. What that translates to is a total nitrogen load potential, right? These aren't actual numbers. These are just potential loads of between 6,000 to almost 14,000 kilograms dry weight. So almost the same as 2,000 tons of dead fish. So you could actually have doubled your nutrient load in this region during that time. Okay, so the last slide I have is the hangover effect. So we think that this unprecedented loss in seagrass and macroalgal macroalgal proliferation is tied to not the red tide, not the hurricane, but what happened afterwards. And so this idea of dead fish plus dead seagrass is kind of this 1-2 nutrient punch. What somebody said was a 2-night out bender, hence the hangover effect. So a lot more work needs to be done to kind of solidify some of this, but this is sort of our working hypothesis at this point. And next slide. I just wanted to thank all our partners. Like I said earlier, we can't do our job without all of you. So, this is a group effort, and, really just really professional, really hardworking, passionate folks went into making this presentation. Next slide, and that's it. So that's my contact info. If we do run out of time and there's any questions, you can get a hold of me. Thank you. All right, now I'm going to put my session lead hat back on, and I'm going to introduce Jennifer Shafer, who we heard in the last session. Jennifer, I don't know if you got an introduction, but I'll go ahead and do it anyway. Dr. Shafer is the co-executive director of the Science and Environment Council. It is a nonprofit consortium of 40 science-based environmental organizations serving both Sarasota and Manatee County. And so what she's going to talk about in this session is best practices for regional coordination of emergency response to severe red tide bloom events. There's that slide. There's that picture.
I know. Thanks, Chris. There's that slide again. Well, I'd also like to introduce one of our project collaborators, Alana Todd, right here. She is the environmental planner at the Tampa Bay Regional Planning Council. She'll be available for questions as well. So today we'd like to share results from our 2018 Tampa Bay Red Tide Impact and Response Assessment, where we examined the impacts from the massive 2018 red tide bloom, and we documented the county level emergency response. Since our report was released, we've experienced yet another severe red tide bloom, as just described. So as a bonus, we can also report on how the region has really stepped up its red tide response game. Next slide. So Florida red tides caused by a bloom of the dinoflagellate Carenia brevis, which produces brevitoxins, nasty neurotoxins harmful to humans and lethal to wildlife. The low-level blooms of red tide occur along the southwest Florida coast in most years, hence it's known as a naturally occurring algae, but the intensity, extent, and duration of the 2018 bloom was unprecedented in recent years and received national attention. Next slide. You can hit this QR code to get this David Shafer original infographic and the full 2-volume report. In the fall of 2018, the red tide cell concentrations rose to 1,000 times lethal levels and stayed there for weeks on end. The result was devastating. Manatee, dolphin, and turtle strandings were up 300%. Calls to FWC's fish kill hotline up 400%. Altogether, over 2,000 tons of dead marine life were collected from Tampa Bay area beaches and waters. Human communities were impacted too. Manatee County Barrier Island restaurants lost 27% of their gross revenue for the year. Visitor lodging was down 18% for Manatee County. And 211 calls for social services were up 471%, especially for food, utilities, and housing. Manatee County, in fact, reached a 3-year high in October of 2018, and this was higher than what was experienced during Hurricane Irma the year prior. Next. We also wanted to find out what was happening on the front lines of the red tide response. We interviewed emergency response managers and natural resource managers from each of the 5 counties of the Tampa Bay and Sarasota Bay region. So Pasco County, Pinellas County, Hillsborough County, Manatee County, and Sarasota County. Given the extreme conditions, the response from these county managers was remarkable. They worked collaboratively and creatively to adapt and implement new strategies to respond to these rapidly changing conditions. It was a privilege to be able to speak with them and for them to open their office doors to us. Next. So with our regional perspective, we were able to identify notable actions and innovations, see where there were gaps and challenges, and provide some recommendations for preparing and responding to future red tide. We use this information to generate custom red tide response operations plans for each of the 5 counties, incorporating detailed steps for monitoring and reporting, cleanup, communications, and records management. Next. So I want to give you some examples of the challenges in red tide response and some recommendations for possible approaches. This is just a sample of what's in the full report. So on authority and coordination, one big gap was in funding. The governor's declaration of emergency came weeks after impacts started, delaying the release of DEP funds, Florida Department of Environmental Protection, that counties needed to activate their cleanup contractors. Then counties did not have a formal process for coordinating response efforts between neighboring counties, except for sharing situation reports on their weekly calls. And since red tide impacts moved northward up the coast and were spatially patchy, even in affected areas, not all counties were responding to the same intensity at the same time, leaving some resources unused and some counties struggling to find equipment. None of the 5 counties in the Tampa Bay and Sarasota Bay region had a red tide response emergency plan prior to the incident. There was little institutional memory from the last major red tide event in 2005-2006. And so as a consequence, staff were tasked with creating and adapting procedures really on the fly. It was quite remarkable. So some recommendations for possible approaches. Develop a process with DEP for determining what conditions trigger the release of grant funds in order to activate an early and robust response. Developing a process or MOU for cooperation between neighboring counties for mobilizing surveillance equipment and subcontractors in shared water bodies. And developing and adopting county-wide red tide response operations plans. Next. Conditions assessment. Counties developed their own procedures for daily assessment of conditions, offshore, inshore, and onshore, such as estimating debris volume, water color, respiratory irritation, and odor. Standardizing these subjective qualitative measurements among observers was challenging, and it wasn't consistent across counties, so couldn't be compared. And because of the complexity of operations, there were different data streams being reported to different managers in different formats. And overall, it seemed most counties lacked a centralized open data reporting, management, and visualization tool, such as what was developed for Piney Point by the TVEP. So some possible approaches include developing a regionally standardized SOP for open water and shoreline surveillance, especially for those qualitative indicators, and developing centralized open data management and visualization tools. In the midst of the crisis, you want reporting tools to be simple and fast for staff to use and use consistently, and you want data summaries and visualizations readily accessible by leadership. Next. Cleanup is at the core of red tide response, and perhaps the single most important tactic is tracking floating debris masses and removing them before they impact shorelines or sink to the bottom. Besides the obvious impacts to beaches and sensitive coastal marsh, dead fish left to decay in the water may contribute to a longer red tide bloom. They may cause more severe water fouling that may be responsible for seagrass die-offs and increased long-term nutrient loads in the bay, the so-called hangover effect. So this was in fact Pinellas County's strategy. They were a leader in this, and you can see the payoff. Using a variety of vessels and manpower of local fishermen and charter captains, over 1,800 tons of red tide debris were cleaned from Pinellas County waters and beaches. Some counties couldn't get the specialized vessels, tools, and staff that they needed to do open water cleanup. The job was just too massive. Next. So after our report was released in early 2021, Alana Todd with the Tampa Bay Regional Planning Council took the lead to organize and facilitate coordination on red tide response. She organized a red tide response working group for the region and convened a workshop to prioritize which of our recommendations along technical or procedural or policy lines would be most effective and helpful. Next slide. But red tide struck again. Within days of our workshop, another severe red tide bloom began to grow out of the Piney Point spill in Tampa Bay, as Ed described. And this FWC cell count map shows the severity and extent as of July. Next. While the 2018 red tide event did not migrate into Tampa Bay, the 2021 bloom was different. Conditions inside the bay fueled the worst red tide for middle Tampa Bay in 50 years. But with our biweekly meetings with regional responders already scheduled, we were in a unique position to support a collaborative meeting space for the response. And we can also make some observations now about how the 2021 red tide response compared to the 2018 response. Next. So improvements for 2021 include surveillance. 3 counties added drones to monitor their daily conditions. Cleanup. 2 counties added capacity for open water cleanup. Information sharing. The biweekly calls that Alana had organized had representatives from 6 counties, 2 estuary programs, and FWC. These were really an important forum for reporting and discussion, where participants could ask questions of each other, and especially Kate Hubbard, Dr. Kate Hubbard, FWC's red tide expert. Kate also provided a daily roundup of monitoring data by email each evening. I don't know if she's online, but shout out, kudos. It was an amazing effort. We'd get these emails at like midnight after we'd all gone to bed. Operational readiness. Counties used all the experience from 2018 to quickly prepare and activate the response. Some now have formal operations plans. Regular aerial surveillance for hotspots got resources where they were needed most, and dashboards were used for information sharing. Next. So, comparing the 2018 and 2021 responses in terms of tons of debris removed and costs as measured by FDEP reimbursement grants. The 2021 event was again very severe for Pinellas County, but their response was much more efficient. On a cost per ton basis, all the counties did more for less. In fact, Dave Tomasko and I did some back of the envelope calculations, and we found that removing fish from the bay is more cost effective than typical stormwater BMPs in terms of pounds of total nitrogen removed. For Pinellas County's effort, it was on the order of about $100 per pound of total nitrogen. Again, back of the envelope, this effort from Pinellas County to remove that tonnage equates to about 12 metric tons of total nitrogen. Again, back of envelope needs to be verified by folks who know. But as an order of magnitude, you can kind of see the impact of getting that floating debris out of the water before it hits beaches, before it sinks and adds to the debris, the nutrient load. Next one. All right, looking ahead. Counties still need more vessel capacity. They still need more staff training, especially for standard operating procedures around assessment and around tracking expenses for grant reimbursement. More capacity is needed for aerial surveillance. And as Pinellas County reported, they need a specific red tide RFP in order to get the right contractor with all that specialized equipment and crew ready to go, separate from, for example, their hurricane debris cleanup contractor. And finally, everyone wants a faster grant process. They don't want to be stuck in a logjam of paperwork for FDEP grant reimbursements when they're in the middle of an emergency response. Next. So bottom line, it's all about targeting the floating debris. Red tide and marine life do not stop at the county line. And it's actually pretty challenging call of duty to get out there and do that, but it can be easier and more effective with regional cooperation for data sharing, for sharing equipment, contractors, surveillance. and with technology that can more precisely target cleanup efforts and that can help coordinate regional managers and provide better communications to the public. So cooperation can lead to more capacity leads to more cleanup, and that leads to a healthier bay and a happier public. Next. So we'd really like to sincerely thank all the scientists who shared their data and the managers who opened their offices and talked to us about that very traumatic time and all of the innovation that they did made this study possible. We're grateful for funding from the Tampa Bay Environmental Restoration Fund. And you can find our full report at scienceandenvironment.org/redtide. Thank you.
Thank you, Jennifer. Okay, so last but not least, we have Dr. Mark Fonseca, who is going to be talking about separating the norm, detecting extremes and resilience thresholds. Mark started in the summer of 2012, he joined CSA Open Sciences Incorporated, and he became the vice president for science in 2015. And he's been providing leadership over all aspects of CSA, science, staffing, and quality. I remember, and I think many of you know Mark from his years of work with NOAA, both the National Marine Fisheries Service and the National Ocean Service as a research ecologist. So without further ado, he is joining us virtually. So Mark, I'm gonna hand the controls over to you.
Okay, very good. Thank you. Can you hear me okay?
Yeah.
Okay. Well, good morning. It seems like it's only been a short time since we were together, but in the next 12 minutes, I'd like to explore with you the anatomy of an extreme event. It resulted in landscape scale changes in seagrass abundance. It's one of the few instances of which I'm aware where there's a well-defined exceedance threshold that was met and an accompanying loss of seagrass in response to a natural event. Next slide, please. So to start off with, I thought I'd talk about what is an extreme event. Typically, I think we can think of them as having 5 components: their severity, their extent, their duration, their frequency, and the sequence in which they occur. Next. Their characteristics are often abrupt and sometimes rare, usually rare, but they're also hidden by measurements of central tendency, such as means, and they are characterized by exceeding a critical threshold. And finding thresholds is really what helps us understand whether or not an event is actually a clock setting or catastrophic event. Next. Usually, we can use simple diagnostics, such things as measuring intensity from cumulative frequency distribution of the events, and we can examine event duration, also as a function of intensity. In other words, how long is, for example, storm events I'll be talking about today, how long are they there? How long are they grinding on the environment? Next. We'll have I'll talk about 3 elements of this today: the severity, duration, and frequency. Geographic extent for big storm events is usually not an issue for some of the resources that we may be looking at on watershed bases, and sequence is a talk by itself. So next slide, please. More event terminology. It's also a matter of scale. You know, we hear both disaster and catastrophe sort of used interchangeably, but I don't think they're the same thing. A disaster is comparatively localized. It's presenting a selective pressure, leaving certain representatives to repopulate the habitats at perhaps a landscape scale, versus a catastrophe. A catastrophe is just disaster plus. It's so widespread and so severe that there are no representative left to populate at a landscape scale. Next slide. So I'm going to take you out of Florida, and I'm going to wind back the clock 31 years to something we're working on. There was a 4-year survey we're doing of North Carolina seagrass landscapes. And in the middle of this, we had the 1993 storm of the century, and it eradicated many of our sites. Next. Well, we thought we were hosed. We saw the storm coming. Oh, and the talk's over. So we asked, but was this a catastrophe? We lost many of the sites. It turns out it was probably the most interesting thing that happened in the entire study. Next slide. So quickly, the storm of the century happened in March of 1993. It was the equivalent of a Category 3 hurricane, but it happened in March. It stretched at one point from Honduras to Canada. And the red dot shows you where we were on the North Carolina coast conducting these studies as this large frontal system passed across. Next. So this is sort of the heart of the response, and I'll try to walk you through it in terms of the effect on seagrass landscapes. Here we have 4 panels, and these are 4 examples of a time series of 50 by 50 meter plots. And these, so each one of these panels is a site, but just with repeated samples running counterclockwise from upper left across the bottom to the upper right. These 50 by 50 meter areas were selected. We had 16 sites across a wave energy gradient, and we manually mapped them at 1 meter resolution in the summer and fall of 1991 to 1995. And if you look at the upper left panel, the very, very upper left panel is the summer of 91. Next would be the fall of 91. And it keeps repeating, summer, fall, summer, fall, summer, fall, all the way around to 95. And this is a very low wave energy environment. So you can see there was no real change in the seagrass cover, which is, of course, the dark shading. If you go to the lower left, with a representative wave energy of about 277, which is actually joules per meter of wave crest, we see that the site pretty much stayed the same through this period of time. If you go to the lower right, even more wave energy, we see that this was an inherently patchy environment that did change over time. And the upper right is one of our most wave exposed locations. And if I could have the next advance, this shows the timing of the March 1993 event. So going back to the upper left panel, nothing really happened on either side of that as you go from the upper left to the upper right in a U-shaped pattern. If you go to the lower left, if you were able to squint closely, what you would actually see is a lot of the very small patches got winnowed out on either side of the red line. In the lower right, the next most exposed location, only the larger patches remained after the storm. They were essentially being ground from the edge towards the center. So the storm, this particular storm, was of a threshold of duration intensity that beds with a certain degree of patchiness could still survive. But in the upper right, it was so extreme that it eradicated the seagrasses over thousands of acres of the estuary. Next slide, next advance. So what that looked like, the relationship of percent seagrass cover on the vertical axis as a function of wave energy before the storm, was a pretty good fit of relationship of seagrass cover declining with increased wave exposure. Next. But if you looked at the same sites and plotted them after the storm, you'd get a curve that looks more like this, predicting that above a certain wave energy, around 1400 joules per meter wave crest, you wouldn't expect to see seagrass habitat. So this means if you had done a survey at one point in time versus another point in time, you may have a very different perspective on what constituted seagrass habitat in the system. Next slide. So let's dig into it a little more. Let's bin up this information and try to understand where the storm fell in the frequency of events. What I did was I took all the wind data from stations along the North Carolina coast and summarized them into wind speed percentiles, the 95th percentile, the 99th, 99.9th. You know, this means that at the 95th percentile, 95% of the wind speed, hourly wind speed observations fell at, in this case, at 24 miles per hour or below. And obviously, as you go up in your percentiles, those thresholds also increase. But it also means there's a very different frequency of events. At the 95th percentile, basically, we'll have 32 events per year that exceed 24 miles an hour. And the average interval between those is about 12 days. But for some of these really higher wind speed events, we have few events per year, and on average, over a year between when these events, wind speed events occur. Next slide. So let's apply cumulative frequency distribution to one of the closest site to where we're working, which was Cape Lookout, North Carolina. So here I plotted up 33 hours of hourly wind speed observations in a cumulative frequency distribution. And you can see where these numbers for the percentile bins come from. You run up on the 95th percentile, which is on the horizontal axis, run it across to wind speed, and that's 24 miles an hour. 31 miles an hour, 42 miles an hour. But then when we put the sustained wind speed of the March 93 storm on that, we can see that that storm event was extremely rare. It was closer to the 1/100th of 1% of all the wind speed observations that were ever seen at North Carolina. Next slide. So what about duration, the time above a percentile? We just look at the storm as it came through North Carolina, the wind speeds on the vertical axis and time across the bottom. It lasted about 30 hours at the 99th percentile wind speed. It lasted 14 hours at the 99.9th percentile wind speed. So it ground on the system for a very long time at wind speeds that were extremely rare, at either 1% or 1/10 of 1% of the kind of wind speeds that were ever seen. And it took that kind of event to effect the change in landscape that you saw in a couple slides ago. Next slide. So storm duration is the other part. It's not just how intense it is, how long does it grind? If we go back to these percentile categories, 95th, 99th, 99.9, and bin them into duration bins, 5-hour durations at that speed, 10-hour durations at that speed, etc. We see obviously the percentages decrease because the storms, those events get rarer, but on average in the 95th percentile, and it's about 20% of our events are, the average is about 20% of our events in any duration bin, and that all decreases. So there's a decrease in the percentage of storms with increasing duration, irrespective of what wind speed threshold you look at. Next. For the 93 storm, back please. Thank you. The 93 storm was extremely rare. It was a long duration event, landing in the bins of the rarest, highest wind speeds. So it took this kind of rare event to essentially effect a change. Next slide. So to conclude, what I want to say is that the March 93 storm was at the extreme limit of wind speed frequency and duration in the North Carolina systems. And this exceedance of these rarely met thresholds is what was needed to occur to actually precipitate a landscape scale loss in seagrass abundance. And we asked the question, but was this a catastrophe? As it turns out, no. We think that this was a disaster because the system was resilient. There were landscape survivors and patches reestablished in those areas that had been rubbed out within about 4 to 5 years. To generalize, though, to go beyond just this North Carolina example and talk about what we're and get to what we're talking about in this session about episodic and catastrophic events. Next. The general take-home points is that identifying these thresholds and knowing what an extreme event actually was that took to precipitate a change changed our perception of system drivers. This effect of system rebooting had really important implications for interpreting your surveys, as I mentioned before. The intensity plus duration plus frequency of this storm event would have given regulators a very different perception of what constituted manageable seagrass landscapes. But this couldn't be done without continuous data. And this was the hourly wind speed data that we were able to delve into and tease out these values. Sparse data, monthly wind speeds, monthly sampling, could not detect these kinds of events. And not being able to find that threshold and understand what would really make a change in this system has an extreme potential to mislead management decisions as well as misinforming ecology. So I guess my big take-home point is we need to design surveys and data analysis to detect ecological responses to extreme events at the scales in which we're managing them. And thankfully, this happened in the middle of our study. Next, and thank you.
Thank you, Mark. And thank you to all the presenters in this session. Thank you guys for hanging in there. I think we're over time. So I know I'll hang around for a few minutes. If anybody has any questions, I'm sure the other speakers that are here physically will be around.